When I first started in networking, 100 megabit was somehow a commodity, and gigabit was somehow the latest and greatest. Transceivers at these days were more like a line card thingy. They were pluggable, but you had to remove the entire line card. And looking at Google's data centers, they had a top-of-the-rack switch, which was at these days a broker of 4,000 from HP. Now, this was 20 years ago. I got a little bit older as well, and started also working on technology which we are having today. Like 100 gigabit is becoming more and more commodity, and the latest and greatest is 400 gigabit. Transceivers are no longer line cards. This is more a pluggable module, really small, and I'm pretty sure Google doesn't run any broker of 4,000 any longer. I think they are in the museum by now. The switch is not Google. But what also has changed is definitely the complexity of your network, and also even single component within the network. And one part is the pluggable transceivers. They can also cause you some headaches, not only the transceivers, but actually the complexity of the entire setup, because it got way more complex. And that's the talk basically about it, to understand a little bit more the innards of especially the transceivers, that you can imagine or that you know where trouble is coming from. So what I did here for you is I have to put that a little bit away. I made a comparison just I opened up two transceivers. The first one is on the upper one is 10 gig SOP+, and below there you see one of the latest developments on 400 gigabit transceiver. And beside the size, there's also the innards look pretty much different. For sure there's a PCB and some microcontroller on there, but I don't want to focus on the microcontroller. I want to focus on the DSP in my talk, the digital signal processor, and the two golden boxes there, the transmitter and receivers, which got a little bit bigger. And here you can also see where this artificial word transceiver is coming from. Transmit, receive, combine it, you get transceiver. So let's start with the transmitter, which is when we have that golden box of a dimension of 5 by 10 millimeters, and that's really important to remember while I do my talk. It's really small. This transmitter is also called in the optical industry the TOSA, which stands for the transmitter optical sub assembly, and you see now why. At the beginning there is the electric connector to feed in our signal into that box, and now the box is still empty, so we have to place some components in that box. And the first one for sure are the laser diodes. As we are talking about 400 gigabit, and we are pretty much aware that 400 gigabit is mainly achieved by 4 times 100 gigabit, so we need 4 laser diodes in there. These laser diodes typically do the conversion from the electrical signal to the optical level, and we get out some light. I would call it just light, but it's not focused, it's not directed, it's light. And another thing about the laser diodes is they consume power and they get heated up a little bit, although these are diodes, but they still dissipate some heat. So we need a cooler in there. This cooler really keeps the laser diode stable, and what is stable is the wavelength. So we want to keep the diodes on a certain temperature, that the light that they emit is in a certain spectrum of light. And if we don't have that, they drift away, and when they drift away, that's nothing we don't want to have. Now, so we have now the diodes which are cooled, which are emitting our proper light, but it's still not focused. So to focus, like everyone knows, for the audience who is wearing glasses, you also need that as well to focus. The transceiver needs this as well. We need 4 of them, so it's a half spider. We have optical lenses in there, so they focus the light going through a certain direction. So in this case we have 4 colors, 4 light beams, but as you can imagine, this doesn't hit the receptacle on the right side properly. One word about those lenses, just to get a rough idea how big they are. They're a little bit smaller than the ones you wear on your nose. They have a dimension in XYZ of 0.5 millimeter, and you have to get them positioned quite accurately in XYZ in steps of 50 nanometer. And when you got the right spot there, when they're in focus, then you have to fix them. And they have to stay there for the next couple of years or decades. In production, this is mainly done with glue, which is hardening with UV light. And that's one big challenge there, to get the proper glue that it stays there also for the next 10 years in the same position. Because otherwise, when the lens is going to move or moving away, then your laser is out of focus. So those 4 beams need to hit somehow our fiber on the receptacle, and we get an optical multiplexer in there. Within that multiplexer, we got 4 filters, and this filter block pretty much works like a little bit like mirrors. So we bounce the light beams back and forward from top to bottom and insert it to the receptacle. So now we have the 4, and that's a purely passive device, like a mirror as well. So we have now the 4 waves on our receptacle and can hit the fiber. And going on the fiber, on the other side, we have to receive it as well. As you can imagine, we have also a ROSA, which is the receiver optical sub assembly. And again, it's an empty box. And it almost works the other way around. We got an optical demultiplexer, which separates our 4 wavelengths. Again, because they are combined, and now we have to separate them via filter blocks. So how does this work? It gets into the multiplexer, and for example, the green light is only passed through the green filter. The other colors are bouncing back and forward down the row. And when it's on the certain gate or the certain filter, like the blue, red, or yellow, it's separated there and filtered. So now we have 4 separated colors or different wavelength, and they're gonna hit a optical lens again, because it's the other way around. So we get it focused again here. So now we have the whole spider with 8 eyes hitting a pin diode. This diode is actually the opposite of the laser itself, so it does the conversion from the optical light level to our electrical signal. But the signal which we get out of that diode, it has a really low amplitude, and this amplitude we can't do any post-processing so far. So to boost that up, we need an amplifier, an electrical amplifier, to boost up the electrical signal that the post-processing from the DSP or also the signal influencing components can handle that electrical signal. One side story here, when you might have came across when you were running 10 gigabit transceivers on a long span up to 80 kilometers, and you didn't put that much attenuation on that receiver, some people burned their transceiver. Actually, because the receiver got too much light in there. But actually what you burn there is not the diode, you burn the amplifier. Because what happened, the diode got too much light in there, the incoming signal to the amplifier was too high already, and so at the end of the day the amplifier burned. So ending up, your transceiver was, or the receiver diode was still operational, but the amplifier was broken at this stage. Okay, and then back to the PCB to do some post-processing with the DSP. Now, these are the 2 components generating and receiving the light. When it comes to production, I want to point to a certain direction, and I also want to point to Brian's talk this morning about testing, and that's, I think, also in the environment, assembly and testing of transceiver, an important thing. And I brought up that graph here for you to get a rough idea. You get on the x-axis, I have 3 sections. It's the 10 gig transceivers, 100 gig and 400 gig one, and then on the y-axis it's the timing in minutes. And there are 3 lines. The blue one is basically the assembly, which is straightforward. So 10 gigabit transceivers are, let's say, fast to produce. 100 gigabit takes a little bit longer, and a 400 gigabit transceiver, for sure, doing it in mass production in batches is roughly 25 minutes to build a 400 gigabit transceiver, combining all the components together. But the interesting part is the green row. It's the testing. So at 10 gigabit, it was nearly the assembly time, so the overall time building a 10 gigabit transceiver and test it is roughly 8 minutes. Now at 100 gigabit and even 400 gigabit, the testing, there's a way steeper rise going up there to do the testing of all the components inside the golden boxes I showed previously, and also the overall setup of the transceivers to have at the end of the day a reliable product which will last for a while. So this ended up for a 400 gigabit roughly at 2 hours. So one single piece needs 2 hours of processing, but the major part is the testing there. And as also Brian mentioned this morning, testing is something, yes, you need a proper blend, but if you test the wrong stuff, it doesn't help you much. And just one example here in testing is when we look at the temperature. So this is one test case you do there in temperature. You see there my 2 artificial TOSA and ROSA. So on the left side, this building block thingy there is the with the green, blue, orange, and yellow brick. That's the TOSA, and the other one, this construct there, is the ROSA. When you operate it at 0 degrees temperature, Celsius, then, for example, one laser drifts away, like in this situation, the green one. It's gonna drift away a little bit, but it might stabilize after a while. And then on the other side, you operate the same transceiver at 70 degrees centigrade. All components are working fine, but the green laser again drifted away the other way. So this is one test scenario. But the more interesting one is when you put the time in there as well. So what we do in production is we start at room temperature at 25 degrees, we cool it down within 30 seconds to 0 degrees and measure over that period of time how does it behave. So when my laser stabilizes after 5 minutes, but my threshold to get it there is 30 seconds, it's a failing part. Although it made it someday or after 5 minutes, but we want to have it done in 30 seconds. And then the other interesting measurement is we ramp it up within 45 till 60 seconds up to 70 degrees centigrade and see how all the components inside behave. And that's also a good way to see if everything works smoothly, and if it takes too long to get a bit error-free transmission there, or the wavelength is shifting away and is not coming back again, then, for example, the cooler made a problem there. So that's one scenario. So when there is testing involved, there are basically, I would say, 2 types of testing. For sure, you can do testing, but if you do it with the wrong metrics, you get a result, but it's not very helpful. So you precisely choose the metrics you want to test there, and that's one of the major parts why the rise of the testing, the green curve I showed previously, is so high, and we take that much time for that. Another example, and therefore I use this artificial horse-driven crane lifting up a weight. So on the left side there is a horse spinning on the wheel, and we got a little bit of gear, and this is lifting up that weight on the right side. If the tiniest gear wheel is breaking, the entire crane won't work at all, and it could be even worse. Like here in that scenario, the weight could also destroy something else. And this is also to bear in mind when you look at the complexity of those components. If one component in the innards of the TOSA and ROSA boxes will fail, it can also influence other components to fail. Failures, good point. I got the message to slow down, okay. Failures. When it comes to operate 100 gig or 400 gigabit transceivers these days, a new thing was, I got confused. The goal is to have production, green light, everything is fine. But now, coming to forward error correction. So when you operate a 100 gig or 400 gig link these days, you want, first of all, you want to establish the link. That's the first thing. And the second one is you want to have a bit error-free communication. In 10 gig or below that 1 gig, there was a thing called the cycling redundancy check, the CRC, which was part of the Ethernet frame, which took care at least for detecting errors in a frame. Now with 100 gig and 400 gig, this won't work any longer. It's still in there because it's Ethernet, but we need a little bit more technology there to detect and to correct errors. And that's the forward error correction, also FEC called, and which is part of the DSP or on the switch side. So in general, let's start with the 100 gig one, is we have our 2 switches on the left side and the right side, and the left FEC does does encode our payload, transmit it over the line on the right side, and then the FEC also does some magic to decode everything again, and we get a bit error-free communication there. So far, so good. But in general, how does this work? I have here kind of a scenario. On the left side, this is our encoder, that's the truck or the lorry, and he has a payload with bits there, the bricks inside there, they're somehow in order, and on the right side we have an excavator, which is our decoder. That's the proper tool to get everything in order again. And the second step, the lorry hits the road, it's a dodgy road, it drives there, and the bricks get somehow disordered, and even one bit was missed, or dropped on the line. And on the third one, the lorry hits the excavator, so on the receiving side, and then the excavator brings all the bricks in order. I don't know how he made it to get the lost brick in order, but he made it. And that's pretty much the FEC works in general. It can, so when you assume you have an Ethernet frame of 1,500 bytes, which are roughly 12,000 bits, and in the best circumstance, when all the errors are equally distributed all over that frame, it can correct up to 330 bits. In the worst circumstance, when they are clustered at a certain spot, you can only correct 33 bits of that single frame, but it's still quite powerful. How is it achieved or done? There are different ways FEC can be implemented, but the typical one for 100 gig and also for 400 gig is the FEC, and that's where the DSP comes in place, increases the bandwidth a little bit of roughly 3%. So when you're having your 100 gigabit, which is actually 103.125 gigabit on Ethernet, it goes up the speed of 106 gigabit. And the overhead of 3 gigabit is only for the FEC reserved to add additional bits there to feed into the FEC algorithm. As I already mentioned, we have the 400 gigabit. In 400 gigabit, it looks a little bit different. We still have the 2 FECs on our switches implemented, but also on the transceiver side, there is a FEC now involved. So in total, we have 4 FECs and not 2 any longer. So how does this work? The FEC on the switch starts to encode our payload and transmits it over to the transceiver. So we are not on the line yet. We are still in the switch. The transceiver decodes this signal and encodes it again, brings it on the line, and on the other side, the other way around. So the transceiver has to decode the counterpart transceiver's FEC, encode it again for the switch, so that the switch can decode it again. And we have the whole path, set it up. This brings also some challenges there. So the FEC, first of all, there needs to be made a decision, when is the FEC in place? And typically, when we look at 100 gigabit, it was typically that it was made on the type of transceiver, the type of standard you want to use. So for example, 100 gigabit SR4 or CWDM4 required a FEC on the switching side, while LR4 didn't require a FEC. So based on the programming of the transceiver and also how the switch recognized it, the switch enabled the FEC or not. If he wasn't enabled, or if he didn't enable the FEC, or if you have 2 different switches from different vendors, and one vendor enabled the FEC and the other didn't, the entire link didn't come up. So, and that's really one learning. When there are FECs involved, it's always important to have an equal amount of FECs. And can also be like 0, no FEC at all. When your link is working bit error free, check. When your link is not working bit error free, you have to make sure that the FEC is enabled on both ends. And on 400 gigabit, the complexity goes up a little bit because you have now the choice enabling 2 FECs or 4, but never do 3 and never do 1, because then your link won't come. And that's also a finding, and this will help in 400 gigabit, when you have a link and it's working, but you have bit errors on it, you might double check the settings of the FEC, especially the ones on the transceiver, because it will be for sure that in 400 gigabit the FEC on the switch side will be enabled by default. There is no choice any longer. It will be interesting to see where the transceiver FEC will go, if it will be enabled or not, because the drawback of FECs is, the nice thing is they can correct errors, but on the other side they need power, and power is also heat. And plus the fact they will add a little bit delay to our signal there. So it's important to choose the FEC wisely in that stage. Finally, before what is coming out new, and also things have changed in the high-speed transmission path so far. I did last year a talk about general 400 gigabit, what we will see there, how the setup will made of SR4, SR8, DR4, etc., different distances, and also with the modulation. And it's still an open question about even standardization about 400 gig LR4. It's not solved yet, and there are mainly two solutions out there. The one is CWDM4. Why do I mention it? It's like the CWDM4 has a spacing of each laser running, or a spacing of 20 nanometers. And that's mainly driven by the industry. The industries would like to have it. But talking to IEEE, they would like to stick to a solution which is known from 100 gigabit LR4, which has a spacing of each laser wavelengths of 5 nanometer. So it's not sorted out yet which standard will make it at the end of the day. The reason for CWDM4 is, at the end of the day, cost and production timing. So it's cheaper to produce a CWDM4 laser and keep them stable than a LAN WDM 5 nanometer spacing. Also, on a 100 gigabit, we see new things coming up. Although I thought up till beginning of this year that no one will put any efforts on 100 gigabit any longer. And when I mention here 100 gigabit, I mean the nice form factors based on QSFP28, not talking about CFPX. Yes, nice form factors, QSFP28. And so there was somehow, the landmark was ER4 Lite hitting up to 25K, 30K, and there it somehow stopped. Now we see, and we can do testing soon with ER4 40 kilometers or ZR4 80 kilometers, which gives a totally new design, gives you totally new design considerations when you're running straight out of your layer 3 gear 100 gigabit over 80 kilometers and not using a transponder system there for that. And another thing I want to mention is the 50 gig ER, and that's basically a side product or a result out of the 5G development of mobile networks. Mobile networks have the demand to connect their poles and and the antennas, and they have a lot of them, especially in the 5G world. And the industry, especially the transceiver industry, was pushed to get down the costs, and then the 50 gigabit ER was somehow a solution to say, well, we get high speed delivered for a really low amount of money, and let's see how this also involves our data center infrastructure, because I'm pretty sure the ASICs on the switching and routing are capable to handle it, the 50 gig Ethernet at the end of the day. Also on the single lambda we see improvements. Single lambda so far was 10 gigabit, but now single lambda of 25 and 40 gig is out, it's available, and can also run on your typical multiplexer in the 100 gigahertz grid, currently with a power budget up to 11 dB. To sum it up, there's still a lot of freedom for us, especially now for the 400 gigabit with the DSP involved, because now we have two ASICs or computers in there in a transceiver. Previously it was only the microcontroller which we had to tweak. Now it's also the DSP which needs some attention to change settings, especially also with the FEC. And yeah, thank you very much for listening. One disclaimer, all the toys got back to my kids. They didn't complain at all. Thank you very much. And for sure.
Thank you, Thomas. Any questions? No questions?
Okay.
Oh, question from Rob. He's got a mic on anyway, I think.
Hi, Rob Evans from JISC. So this is a really useful introduction to how transceivers are built, designed, tested. As more and more smarts are put into more transceivers, there's a black blob you didn't talk about, the DSP, which is getting ever more complicated and doing ever more. How does that complicate the whole process of manufacturing testing?
It's a good question, though. The DSP, the main part there is the software testing at the end of the day for the DSP. To get the proper software tests there, set it up, that it, yeah, so it's more software related at the end of the day. Okay? Okay.
Any more questions? Thank you very much, Thomas.
Thank you.
Yeah.